Now we'll discuss section 3.2, molecular polarity. And in order to determine molecular polarity, we need to have first determined the molecular shape of the molecule. So the polarity of the molecule is a consequence of first the molecular shape, and then polar bonds that are present in that molecule. And that deals with the electronegativity of the atom. So we need to define electronegativity. And that is a measure of the atom's ability to draw electrons towards itself in the formation of a covalent bond. So strongly electronegative elements attract electrons. And the level of electronegativity corresponds to their position in the periodic table. So here we see an abbreviated version of the table. We have the main group elements, group 1A, 2A, 3, 4, 5, 6, 7A. We don't have the noble gases because they are not electronegative at all. They don't have any ability to draw electrons towards themselves. And so, observing this chart, we see that the higher the block of the atom or the element, the greater the electronegativity. So we see that electronegativity increases as we go from the bottom to the top of the table, and it increases as we go from left to right. And so fluorine and its nearest neighbors are the most electronegative elements on the periodic table. So fluorine's the most electronegative, then followed closely by O and Cl. There's not much difference between these two. Nitrogen is slightly less electronegative, but these are the four greatest or highest electronegative elements. Again, we don't show the noble gases in group 8A because they are not electronegative at all. They don't have any desire to draw electrons towards themselves. Remember that they are pretty unreactive because they already have filled valence shells. And so, in part, the atom's desire to have a filled valence shell causes fluorine and chlorine and the halogens to have a greater electronegativity than the atoms further on to the left in the table. So remember that covalent bonds are when electrons are shared in that bond, and if the atoms are identical, as in Cl2, the electrons are shared equally. Imagine if you were having a tug of war with yourself, a copy of yourself. Who would we expect to win? It would probably be a draw because you're not any stronger than the copy of yourself. And that's the same if we have these two chlorines are pulling on the electrons in the bond. They're both of equal electronegativity. This is called a fully nonpolar molecule because there's no difference in the electronegativity between the two chlorines. It's called a nonpolar covalent bond, and these molecules are considered to be nonpolar. If atoms have similar electronegativity, the bonds containing them are also considered nonpolar. So carbon and hydrogen, even though they aren't identical, they are considered to have very similar electronegativity. And molecules then that contain only C and H are considered to be nonpolar, and they're called the hydrocarbon family of compounds. So if we have a molecule that's composed only of C's and H's, we'll see a lot more of these later on in chapter 6, this is a nonpolar molecule, even though we have different atoms on the bonds. If we have an atom if we have atoms that have unequal electronegativities in our bond, the bond is called a polar covalent bond. So the example here is hydrogen fluoride, HF. We can see the hydrogen bound to the fluorine. This is an electron density map. The more blue area means there's more positive charge. The redder area means there's more negative charge there. Certainly looking at our electronegativity table, fluorine has much more electronegativity than H. Fluorine is the greatest, the atom with greatest electronegativity. And so within this HF bond, the fluorine is pulling the electrons towards itself more strongly than the H is. And so this causes the bond to be slightly polarized, meaning there's more electron density around the fluorine than there is around the H. You could think of it as my little sister having a contest of tug of war with Arnold Schwarzenegger, right? Certainly my sister is not going to win and really has no chance. And that's essentially what fluorine does. It's the most electronegative element, so it pulls electrons towards itself at the expense of its bonding partner. So we get a slightly positive charge on the other atom, slightly negative charge on the fluorine because it has more electron density closer to itself. This is a polar covalent bond. So this leads to an idea called bond dipoles. And again, here we'll show water. oxygen is much more electronegative than either of the two H's, and so we can draw these two arrows that have a sort of a cross at the back side of the arrow, and the arrow points towards the more electronegative element. So we point from the hydrogen to the oxygen, from the hydrogen to the oxygen, and this plus sign at the back here indicates that the hydrogen has a partial positive sign, partial positive charge. And this hydrogen also has partial positive charge, so the oxygen has partial negative, giving water a very polar characteristic. And these symbols here is the Greek letter delta, meaning partial. We don't have a full positive charge on the hydrogen, we just have a partial positive because the electrons are drawn closer to the oxygen than to the hydrogens. And so if we add up these two bond dipole arrows, sort of in vector addition like you would find in a math class, we get this larger black arrow that's pointing from the hydrogen area to the oxygen. Right? It's showing us that the oxygen is partially negative, the hydrogens are partially positive. The electron density diagram shows that as well. There's a red area here near the oxygen, two blue areas near the hydrogens. So the less electronegative atom, in this case hydrogens, have partial positive charges. The more electronegative atom has a partial negative charge. And we call this molecule and these bonds as having a dipole. This bond has a dipole, meaning the hydrogen is partially positive, oxygen is partially negative. The entire molecule has a dipole where it has a region of negative charge and a region of positive charge. Clicker question 3.3. In the following molecule, which way does the dipole point? Remember that it always points towards the region of highest negative charge. So does it point up, down, left, or right? So in this case, the central atom again is carbon. It has some CC bonds down and to the right and down and to the left, and it has a CO double bond pointing up. There's no difference in electronegativity between the two carbons in this bond or the two carbons in this bond, but however there is a significant difference in electronegativity between the carbon and the oxygen. So anytime you see a carbon-oxygen bond, you can understand that that is a polar bond. And so the dipole arrow would point from the carbon to the oxygen. There'd be a region of partial positive charge in this area, region of partial negative charge in the oxygen. So it would point up. Up is the best answer here. So polarity is a continuum. It's a continuum of possibilities with completely nonpolar bonds at one extreme and ionic bonds at the other extreme, where we've actually switched the electron from the sodium onto the chlorine. That's what happens in sodium chloride. We get a positive sodium, negative chlorine. Whereas polar covalent bonds are somewhere in the middle, depending on their degree of polarity. Some can be slightly polar, some can be very polar, like this HF bond. And so they lie somewhere in the middle, somewhere in the middle of the ionic region and the nonpolar covalent region. And so, taking into account the differences in a bond or several bonds, we can decide which is more polar and which is less polar. And we'll see an example of that in a few minutes. So this practice problem asks us to indicate which of the following represent polar covalent bonds, and you show the bond dipole arrow in the direction of the bond dipole. Okay, so here we have an OH bond. We know that oxygen is more electronegative than hydrogen, and so we draw the arrow in the direction pointing towards the oxygen, and we put our plus at the back side of that arrow near the hydrogen, showing that the hydrogen has a partial plus charge, the oxygen has a partial negative charge. So here we've drawn the dipole arrow pointing from the H to the O. Here we have a carbon-oxygen bond. We just saw that in acetone. We'd draw the arrow pointing from the carbon to the oxygen. The plus sign would be near the carbon. Carbon would say delta plus, oxygen delta minus. Here we have an SH bond. This is a dipole. This bond has a dipole as well. It's not as strong as an OH bond because oxygen is more electronegative than sulfur, but we still have a bit of a dipole. And we can draw that like that. Hydrogen delta plus, sulfur, delta minus. So here's a clicker question that asks which of the following bonds would have the greatest dipole? Or another way to ask the question is which pair of atoms in these four choices has the greatest difference in electronegativity? So we have HO, HF, NN, and OO. And I think right away we can rule out C and D. There's no difference in electronegativity between nitrogen and nitrogen, and there's no difference in electronegativity between O and O. So here we have HO and HF. The difference between these two choices is that one has oxygen, one has fluorine. Fluorine is more electronegative than O. Again, it's the most electronegative element on the table. So the biggest difference between these two atoms would be in the HF, right? Because F is the strongest, the most electronegative element. So the greatest dipole is in HF. The second greatest would be in HO. So how do we use this to decide if we have a polar molecule or not? Well, molecules with one polar bond are polar, so HF is polar, as the HF bond is polar, as we discussed. But if we have F2, fluorine diatomic molecule, the FF bond is nonpolar, because the fluorines have no difference in electronegativity, so F2 is a nonpolar molecule. If there's more than one bond, as most molecules have, the shape and the contributions of all bonds must be considered. It seems complicated at first, but I think it's a little bit easier than you might think. So for instance, CO2 has two polar bonds. The CO double bond to the left, CO double bond to the right. But we know from the Lewis dot structure and Vesper theory that CO2 is a linear molecule. Therefore, the bond dipoles are equal, but they're in opposite directions, and so they cancel out. So this is actually a nonpolar molecule because it's very symmetrical. How about water? Like CO2, water has two polar bonds, OH and OH, but water is a bent molecule based on Vesper theory, right? There are two lone pairs on the oxygen. Those take up two spots on the tetrahedral electron geometry, giving us a bent molecular shape. And so the two dipoles point not in opposite directions, but more or less along the same direction, giving us this overall orange dipole arrow. Partial negative on the oxygen, partial positive on the H's. And so the net dipole is positive towards the oxygen. I'm sorry, positive meaning we have a net dipole. It points toward the region of negative charge. So molecules are usually nonpolar if all the covalent bonds have identical polarity and the electron geometry is the same as the molecular shape. So those are key. Electron geometry, same as the molecular shape. Covalent bonds have identical polarity. So let's look at CO2 again. The covalent bonds have identical polarity, and it is a linear electronic shape and molecular shape. So it's a nonpolar molecule. So if we have tetrahedral molecule, carbon tetrachloride, CCl4, that has all four carbon-chlorine bonds, so they're all the same polarity, and the electron geometry here, tetrahedral, is identical as the molecular shape, tetrahedral. BF3, we have three BF bonds. Those are all the same type, same strength of electronegativity. They're all identical in polarity. And the molecular shape, trigonal planar, is identical to the electron geometry, trigonal planar. CS2, same thing, identical polarity in the two bonds. Molecular shape is the same as the electron geometry. Now, how do we tell if a molecule is polar? Well, first of all, if we have covalent bonds that have different polarity, we have a polar molecule. Here we have chloromethane. We have one CCl bond and three CH bonds. So this is a polar molecule because the bonds are not all the same. Or if the electron geometry is not the same as the molecular shape, basically, do we have lone pairs on the central atom? In water, we have the same polarity in the HO bonds, but because there's lone pairs, the electron geometry is not the same. Electron geometry is tetrahedral. The molecular shape is bent. So the water is polar. Here we have methanol with two central atoms. And we can look at both atoms to decide if the molecule is polar. If at least one of the atoms satisfies our requirement for polarity, the molecule is polar. So here we have a carbon that has two types of bonds to it, CHs and COs. So that leads to this carbon being polar. We have an oxygen here that has lone pairs on it. So its electron geometry is not the same as the molecular shape. So methanol is polar. Here we have acetone. There are two types of bonds on this central carbon, CC, CC, and C double bond O. So it has bonds with different polarity, and it's also polar. Okay, so let's look at this practice problem here. Which of the following molecules are nonpolar? Explain why. Well, first thing to do would be to draw a good Lewis structure. We have a chlorine-chlorine bond, and that's all we have, so this one's nonpolar. And that's because atoms have the same electronegativity. It's a nice long word. How about C3H8? Well, in this case, we have only C and H present, and we defined those to have the same electronegativity. So we have a nonpolar molecule. So remember that hydrocarbons, those molecules that contain only C's and H's, are nonpolar. So SO2, we saw this as one of our examples. We can redraw it quickly. 2 SO double bonds and a lone pair on the sulfur. So trigonal planar electron geometry, bent molecular shape. This is polar because it doesn't have the same electron geometry as the molecular shape. It has different molecular shape. HCl, there's only one bond present here. So the atoms on this bond have different electronegativities, so it is polar. And that's because different electronegativities. And how about CH3Cl? Here the carbon is the central atom. H, 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 Cl. Let me make that bond a little better here. And so here we have different atoms around the central atom. That leads to a polar molecule. Different atoms. We have 3 H's and a chlorine. So that means the molecule is polar. Clicker question 3.5. Is AlCl3 aluminum trichloride polar or nonpolar? So in order to answer this question, it would be useful to draw a good Lewis structure. And I'll squeeze that in over here. Al, and we draw bonds to chlorine. We know that chlorine has 3 lone pairs on it with each bond, but what about aluminum? Aluminum is element number 13. It's in group 3A, so it only has 3 electrons to bring to the table. So aluminum has 3 electrons. And we have 3 chlorines. 3 times 7 equals 21. So 24 total electrons. We already have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So if I give each chlorine a full octet, 3 lone pairs in a bond, I don't have any more lone pairs or electrons left over for aluminum, and so aluminum is left with just 3 bonds to it, no lone pairs. And so that has trigonal planar electron geometry, right? And trigonal planar molecular geometry. So the molecular geometry and the electron geometry is the same, and there's only one type of bond here. There's 3 different aluminum chloride bonds, and so this fits the description as nonpolar. It has the same bonds, and it doesn't have any lone pairs, so it has no the molecular shape is the same as the electronic shape.